Welcome back to Differential Equations. I'm Jeff Groh, and this is Lesson 4. Today we're going to talk about mathematical modeling. Mathematical modeling begins with making a hypothesis. For example, in a simple population growth model, we might assume that the rate of growth of a population is proportional to the population size. From there, we make a mathematical model. For instance, we might write down an initial value problem. The derivative of the population size is proportional to the population size, and the size of the population at time 0 is p0. Once we have a mathematical model, we need to solve the model. The natural growth law leads to an exponential growth rate. Once we have that mathematical model solution, we then compare to data. Does this solution accurately model what it is intended to model? And if it does, then we're done. If not, we need to go back up and make a more informed hypothesis based upon what we've seen. For example, suppose that a vat initially contains 500 liters of water and brine is salt water. Let's suppose it has 0.25 kilograms of salt per liter is pumped in at a rate of, let's say, 3 liters per minute. Brine is removed from the vat at 2 liters per minute. And we're assuming that the brine is very quickly and efficiently mixed. Find how much salt in kilograms is in the tank as a function of time. There are several rates to be considered here. First, I want to define A to be the amount of salt in kilograms in the tank. A lot of people don't appreciate the importance of defining as a variable the thing that you're looking for. Until you do that, you can't write down any equations or solve for that variable. This is a pretty important step. Now, there are several rates to consider here. How is salt changing in the tank? Well, there's salt going in. We're adding salt into the tank. If the tank is over here, we have stuff going in, but we also have stuff going out of the tank. So there's the rate in minus the rate out. The rate in is fairly easy to discern. We know that there's 0.25 kilograms per liter going in, and it's going in at a rate of 3 liters per minute. Liters cancels and we get the number of kilograms per minute entering the tank. How much salt is leaving the tank? Notice that to determine the amount of salt going in, we had to multiply the number of kilograms per liter, the concentration of the salt, times the volumetric rate at which the mixture was being pumped in, 3 liters per minute. The volumetric rate at which stuff is being pumped out is 2 liters per minute. But what is the concentration? That will depend upon how much salt is actually in the tank, and also how much fluid. The amount of salt in the tank is A kilograms. The amount of fluid will change over time because you have 3 liters per minute going in and 2 liters per minute coming out. It starts out at 500, but you're adding 1 liter per minute. If we multiply this by 2 liters per minute, we get the rate at which salt is going out of the tank. The mathematical model for this situation is given by this initial value problem. Note that the amount of salt in the tank at time 0 is 0. What kind of differential equation is this? If we rearrange this, we can put this into the standard form of a first order linear ordinary differential equation. And we know how to solve all of those. The first step is to find the integrating factor mu, which is e to the integral of 2 over 500 plus t dt. This gives e to the 2 natural log 500 plus t. Ignore the absolute value and the plus c in the integral. To eliminate the natural log, we need to bring the 2 up as an exponent. Then we can cancel, and the integrating factor is 500 plus t quantity squared. It follows that the general solution to the differential equation is A equals 1 over mu times the integral of mu q plus a constant divided by mu. The 3/4 can be brought out of the integral, and when we integrate 500 plus t squared, we'll have this 3/4 divided by 500 plus t quantity squared, 500 plus t cubed over 3, plus the constant c divided by 500 plus t quantity squared. This 3 will cancel this, and we can cancel 2 factors of 500 plus t. The solution becomes 1/4 500 plus t plus the constant of integration divided by 500 plus t quantity squared. Next, we need to account for the initial condition that at time t equals 0, there is no salt in the tank. We have 0 equals the amount of tank at time 0. Plugging in 0 for t on the right-hand side, we have 500 divided by 4 plus c divided by 500 squared. We'll move this term to the other side, getting negative 1/4. 500 equals c divided by 500 squared, and then we'll multiply both sides by 500 squared. We deduce that c is minus 1/4 times 500 cubed. This gives the solution A equals 1/4 500 plus t minus 1/4 500 cubed divided by 500 plus t quantity squared. In this particular instance, we don't have data to compare this to, so we're going to leave it at this. I'd next like to consider a population growth model beyond the Malthusian model. You'll recall that the Malthusian model is the model by which Malthus predicted the overpopulation of the planet and vast starvation. This was well over 200 years ago. This is the Malthusian growth law, or commonly the natural growth law. Alternatively, there's something called the logistic growth model. Which says that the rate of growth of a population is not only proportional to the population size, but also 1 minus the population size divided by a constant that's equal to the maximum sustainable population size. This allows for us to model a population having a limited carrying capacity. For instance, you might put fruit flies inside of a box, and if you give them some apples inside of the box, there's going to be a maximum carrying capacity for the number of fruit flies that can exist inside of that box. The logistic growth model is pretty easy to solve because the differential equation is separable. We can separate variables in this way and then simply integrate. On the left-hand side, though, name the method of integration. The integrand is a rational function, prefactored. It's ready to go for the method of partial fractions. To do that, we need to decompose the integrand into pieces like this. Multiplying both sides by the denominator on the left, we have the equation 1 is A times 1 minus P over P max plus B times P. Selecting P equal to 0 yields 1 equals A. We'll put that in a little bucket here. The next logical choice for P is P max, because that will make this term go away. If we set P equal to P max, we get 1 equals B times P max, or B is 1 divided by P max. The integral on the left becomes the integral of 1 over P plus 1 over P max divided by 1 minus P over P max. Note that the derivative of the denominator with respect to P on the second term is minus 1 over P max. We're almost in the form on that term, F prime over F. The only thing missing is a minus sign here. We'll make this into a minus sign here. The integral on the left becomes the natural log of the absolute value of P minus the natural log of the absolute value of 1 minus P over P max, which we can rewrite as log absolute value of P over 1 minus P over P max, which we already know to be equal to KT plus C. exponentiating both sides, we can write this as P over 1 minus P over P max is a constant times e to the kt. Let's define this to be some function f, just for sake of simplicity, when we solve for p. Multiplying both sides by the denominator on the left, we get p is f times 1 minus p over p max, and distributing, that's going to be f minus f divided by p max times p. To solve for p, we need to get all of the p's on one side of the equation and everything else on the other. So we'll move the second term on the right over to the left and have p plus f over p max times p is equal to f. We have two terms on the left-hand side, both of which have a common factor of p. If we factor p out, we get p times 1 plus f over p max equals f. We can now solve for p. P is f over 1 plus f over p max. Remember that f was c e to the kt. We can substitute this in, but it might be better to multiply top and bottom by 1 divided by f. We'll have 1 over f plus 1 over p max. Multiplying top and bottom by p max, we'll have p max divided by 1 plus p max divided by f. We can simplify this as p max over 1 plus a constant of integration times e to the negative kt, where we have absorbed the constant p max into the arbitrary constant c. Now that we have the general solution to the logistic growth problem, we need to account for initial data. Let's suppose that at time t equals 0, the population size is some constant value p naught. Then p naught will be p max divided by 1 plus c. Yes, we have to solve for c, but that's not too hard because we can switch these two. 1 plus c is p max divided by p naught, and then move the 1 over. We'll have c is p max over p naught minus 1. It's easy to see that with the solution to the initial value problem in this form, in the limit as t goes to infinity, the population p will have this term going to 0, and you'll be left with p max. Solutions then will top out at some value p max. If they start here, they may grow almost exponentially to begin with the growth rate slowing and the population tending asymptotically towards the value of p max. One might wonder about an application of the logistic equation to the human population on the planet. Is there a maximum carrying capacity for the human population on the planet? Well, if there is, it doesn't appear that we're very close to it because human growth population throughout the entire planet seems to be still positive. We're on that upward stroke. Some argue that we're nearing the maximum sustaining carrying capacity of the human population because growth rates seem to have slowed, though there are a lot of arguments for and against that. One thing for certain, carrying capacity for this planet, for the human population, seems to have changed over time. So it's unclear that there even is such a thing. I'd like to give an example which is some interest to me since I've been skydiving in the past. Airplane takes you up to about 14,000 feet, where you are summarily pushed out of the airplane, and you fall for about 60 seconds from 14,000 feet to about 6,000 feet, at which point you open your parachute. That 60-second fall, if you think about a ballistic problem with no air resistance, that would put you down around 58,000 feet. However, you only fall about 9,000 feet. The effect of air resistance is very great. So we need to be able to model air resistance. I want to present a model for objects falling with air resistance. We'll have a total force equal to the force due to gravity plus the force due to resistance. The total force, according to Newton, is mass times acceleration. The force of gravity due to Galileo is minus m times g. How about that force of air resistance? Air resistance will satisfy minus kV. You'll have more resistance the faster you go. Anyone who has held their arm out of the car while moving down the road knows that something like this should be true. However, if the object is going supersonic, this should be closer to v squared. So in the subsonic regime, this will be good enough for us. Why the minus? Notice that if the object is falling down, v will be negative. Negative times negative will be positive. The force of resistance should be going up. And that explains why we should have a minus here. We'll assume, as we usually do, that physical constants are non-negative. So far, what we have is mass times acceleration is minus mg minus kv. Let's divide everything in sight by m and rearrange this with this term moved to the left to have dv dt plus k over mv equals minus g. What kind of differential equation is this? Yeah, that's first order linear. Let's add an initial condition that at time t equals 0, the velocity is v0. To solve this, we first need to find the integrating factor mu, which is e to the integral of k over m dt, or just e to the k over mt. The general solution to the differential equation, then, is v equals e to the minus k over mt, this is 1 over the integrating factor mu, times the integral of mu, e to the k over mt, q, which in this case is minus g, plus a constant times e to the minus k over mt. Integrating, we have minus gm over k e to the minus k over mt times e to the positive k over mt, these canceling out, plus c e to the minus k over mt. You can see that as t goes to infinity, on the velocity tends towards a constant value of minus g times m divided by k. That's the terminal velocity in this case. If an object falls with air resistance through the air, it's going to reach some kind of ultimate or terminal velocity. And in this case, you can easily calculate that as minus mg divided by the constant k, the coefficient of friction. What we haven't accounted for is the initial condition. So far, we have v is minus mg over k plus C e to the minus k over mt. If V naught is V at time 0, we get minus mg over k plus C. Moving this term to the left, we get C is V naught plus mg over k. This gives us the final solution to this air resistance problem of minus mg over k plus V naught plus mg over k times e to the minus k over mt. I'd like to talk a little bit about electric circuits. We're mostly going to be dealing with maybe some electromotive force being applied to a resistance and maybe an inductance, or we could have some electromotive force attached to some resistance and maybe a capacitor. The resistor will have resistance measured in ohms. The inductance will have an inductance measured in henries, and the capacitance will have some value C measured in, say, microfarads or farads. We're going to make certain assumptions. First of all, there's Kirchoff's law, which says that the algebraic sum of currents going into any junction point in a circuit is 0. The sum of the currents at a junction point is 0. The basic idea here being that the amount of current going in has to equal the amount of current going out. Second, the voltage drops in a closed loop sum to 0. The idea there being that the electromotive force that you're imposing on that circuit is completely accounted for by the voltage drops through all of the electrical components. We now have to account for the three kinds of electrical components that we're going to consider. First, let's consider Ohm's law. The voltage drop across a resistor is proportional to the amount of current. The voltage drop across an inductor is proportional to the rate of change of current. And finally, the voltage drop across a capacitor is a constant times the amount of charge on the capacitor. Here, we'll suppose that the rate of change of charge is equal to the current I, measured in amps. Let's model. Suppose we have some electromotive force applied to a resistor and then an inductor. The resistance and inductance are denoted by R and L. The electromotive force can be any function at all. That's the amount of voltage applied to the circuit. That has to equal the voltage drops across the various components. The voltage drop across the resistor is R times I, whereas the voltage drop across the inductor is L times di dt, where this is just some arbitrary function. This equation is first order linear. We call equations of this type RL circuits. As another example, suppose we have some electromotive force we apply here, some resistance, and then a capacitor. Again, you have resistance and capacitance. The electromotive force that's applied has to be countered by the voltage drops. For the capacitor, the voltage drop will be 1 over C times Q, where Q is the charge. The resistor will have R times I, but remember that I is the rate of change of charge with respect to time. What kind of differential equation is that? Yep, that's first order linear. And these circuits are called RC circuits. And one more example. In this case, we're going to assume we have an electromotive force, we have a resistor, we have a capacitor, and we have an inductor. If you include all three of these, then the total electromotive force imposed has to equal R times dq dt plus 1 over C times Q. And remember that for the inductance, we'll have L times the rate of change of the current I. That's going to be a second order rate of change of the charge. What kind of an equation is this? These equations are second order linear. I won't teach you how to solve these until after the first test. I'd like to talk about an example of an LR circuit where you have some electromotive force, a resistor, and an inductor like this, resistance L and a resistance R and inductance L. As we already know, the differential equation describing this gives the electromotive force as some arbitrary function, resistance times I plus L times di dt. This is first order linear, but I would like to suppose that the electromotive force is A times, let's say, sine of omega t. In this way, we can put this in the standard form by writing this as di dt plus r over li equals a over L times the sine of omega t, and the integrating factor mu is e to the integral of r over lt dt, or e to the r over lt, like that. It follows immediately that the solution is 1 over mu, which is e to the minus r over lt, times the integral of mu times the q on the right hand side, which is a over L sine omega t dt, plus some constant times divided by mu. With our solution in this form, it appears that we need to integrate integrands of the form e to the at sine of bt dt. Now, this is a classic from Calculus 2, where you perform two integration by parts, end up with the same integral you started with, swing that to the other side, and divide by a coefficient. Now, we could go through the regular old integration by parts, but what I would like to do is show you how to do this integral using the tabular method, even though the no column ends in a 0. To set up the tabular method for integration by parts, we need a u and a dv, I'll choose u to be e to the at and dv to be sine of bt. We differentiate down the first column, yielding a e to the at, and on the second column, negative 1 over b cosine of bt. We differentiate again, yielding a squared e to the at, and integrate again, we'll get minus 1 over b squared sine of bt. We now multiply down diagonals and alternate signs, plus or minus, but because we did not get 0 in this spot, we have to subtract the integral of the product in the last column and affix the previous sign. That gives us negative 1 over b e to the at cosine of bt, followed by a negative negative makes positive, a over b squared e to the at sine of bt, and then we subtract the integral of the product, which is negative, but there's one more thing. We have to affix the previous sign. That gives us 3 negative signs on that term. The integral is now very much like the integral that we started with. We just need to move this term to the other side and combine it with the similar integral. Let's denote this by the original integral I. When we move the integral over, we get 1 plus a squared over b squared times the original integral I equals these other terms plus maybe a constant of integration. This factor here can be represented by b squared plus a squared over b squared times the I here. To get rid of this fraction, we need to invert and multiply so that the original integral is b squared over a squared plus b squared times the rest of this. On the rest of this, we can factor out, and e to the at will have a over b squared sine of bt minus 1 over b cosine of bt plus the constant of integration. Distributing the b squared, we'll have a times b squared here and a times b squared here with just a 1 left over out front. This b squared will cancel. One of the b's will cancel here. The solution then is given here. From this, we deduce that the solution to the circuit problem is a over L e to the minus r over LT times the solution here, which is e to the r over LT divided by, in our particular instance, a was r over L and b was omega, times r over L sine omega t minus b, which was omega cosine omega t, plus c e to the minus r over L t. These cancel, and the solution reduces to what will appear next. There are a couple things to point out about this solution. First of all, this part here is transient. It decays away to 0 as t goes to infinity. So it won't have any long-term, any lasting effect, and should only be affected by the initial data. The rest of this should be a regular sinusoidal curve. Let me state a lemma. Whenever have C1 cosine omega t plus C2 sine omega t, there will exist some amplitude A and some function phi, some angle phi, such that this expression equals A cosine of omega t minus phi. Any expression of this form, some combination, a linear combination of sine and cosine like this, will end up being just some sinusoidal curve with a phase shift and some amplitude. To prove the lemma, suppose I start off with A cosine omega t minus phi. By the difference of angle identity for cosine, we can write that as A times cosine omega t cosine phi plus sine omega t sine phi, or A cosine phi cosine omega t plus A sine phi sine omega t. From this expression, you can see that C1 has to be A cosine phi and C2, cosine phi, and C2 must be A sine phi. To prove the lemma, we need to show how we can construct A and phi from C1 and C2. So we solve for them as follows. In particular, if we take C2 and divide it by C1, the A's will cancel and we'll end up with the tangent of phi. By taking an inverse tangent, we can now find phi as a function of C2 and C1. Alternatively, if we calculate C1 squared plus C2 squared, you square the right-hand sides and add them together by the Pythagorean identity, they reduce to A squared. And this allows us to solve for A as a function of C1 and C2. It follows that any linear combination of sine and cosine can be written as a single sinusoidal function with some phase shift and amplitude.